All right, howdy folks. Welcome back to Professor Carbon. In this video, what we're going to do is talk about some of the complex issues that can come up when discussing how ketones or aldehydes hydrate or form hemiacetals. And so we know that that's an equilibrium process, and it's governed by a number of things regarding what KEQ is. And so just for a quick discussion here, let's go down to the bottom. So if we have our standard old ketone, we know if you have that ketone in water, we can make a very small amount of enol, and so ketone, and then you can have a very small amount of the hydrate as well. And often the hydrate is unstable, and if you remove it from water, it'll shift back to the ketone and give off water. And the hydrate is very similar to a hemiacetal. So if you put the ketone in an alcohol instead, you can establish an equilibrium where you have a hemiacetal. And then occasionally, if you push this forward under acidic and dehydrating conditions, you can form the full acetal. Just going to put R's here, and I should actually go back here very briefly and just delete this to make it an R instead to be more consistent. So then this is the acetal. And in principle, all of these processes are reversible, so we can go ahead and add some reverse arrows in there as well. And the reverse processes, whether they're forward or reversed, is predominantly, especially when looking at acetals, governed on how much water there is around. And so to get it to go forward to the acetal, often we need quite dehydrating conditions. And often the hemiacetals are not stable. So for your average ketone, the default assumption should be that these will revert to the ketone. Same is true for the hydrate. So the default assumption should be that the ketone is the preferred compound in equilibrium most of the time. And part of the reason for that is simple entropy. So if we take two molecules and combine them in an unstable process, we're going from 2 particles to 1 particle, and so that'll shift the equilibrium due to entropy. Often we prefer more particles, especially if it's at elevated temperatures, that delta S times T part of the equation becomes quite important. Okay, there are, however, some exceptions. And so if there's some reason why the ketone is particularly unstable, or if there's some reason why the acetal or hydrate might be particularly stable, we could imagine shifting that equilibrium. So that brings us to this question, which is, there are 3 simple kind of ketones or aldehydes on one side, and then we have some other intermediate, in this case, they're all hemiacetals on the other side, and we might be expected to guess which half the equilibrium will be favored. Now, the easiest one should be the middle one here, and that's because for the simple cyclopentanone, the ketone absolutely should be favored in the equilibrium, assuming, again, that we don't have strongly dehydrating conditions that would drive it to the full acetal. But for your average ketone, you'd expect only a little bit of the hemiacetal at equilibrium. The bottom one here will actually favor the full hemiacetal, and the reason for that is this one's intramolecular. So here the alcohol can't really get too far away from the carbonyl. They're kind of stuck being on the same molecule, and so they will cyclize. It turns out these 6-membered rings with a hemiacetal in them are very similar to our sugars, and so the glucose molecule is one very famous example of this, and it prefers the closed state at equilibrium for the most part. And we actually form polysaccharides from that hemiacetal. The top one here is a fun, kind of interesting question. And remember that your average double bond angle here should be about 120 degrees. And remember that your average tetrahedral angle is 109.5 degrees. And because of that, this sp3 hybridized center has a little bit less what we might call angle strain to go into the full triangle. So if we think about these triangles, we could imagine that that bond angle is quite a bit more narrow than the tetrahedral position. And so that kind of bending of the angle down generates a little bit of angle strain. And because the sp2 hybridized carbon should have a more broad angle, and we're trying to force this down to be the kind of triangle, we can imagine that the sp3 hybridized center would relieve a little bit of that strain. And so for this one, it's going to be a lot closer to 1, and I might circle that the hydrate here might be favored at equilibrium, or sorry, the hemiacetal. And the reason for that is we're relieving some of that strain by rehybridizing that center. And that effect really is not significant until you get to very small rings, mostly in the cyclopropane. All right, so that summarizes a little bit of a discussion here about hydrates and equilibria for hemiacetals. Remember, the default assumption should be that you're going to end up with the ketone at equilibrium most of the time. The only way to push it towards the product really is to have strongly dehydrating conditions. All right, with that, hopefully you're enjoying these videos. Please do subscribe to the Professor Carbon YouTube channel. It's been a real treat to watch that number tick up very slowly, and hopefully it'll continue to grow. It provides a little bit of encouragement to continue to try to make these videos. Again, if you want access to the PDFs of these, either filled out or in the blank format, they're available on our Patreon page, so please subscribe to the Patreon or become a patron follower. Also, feel free to leave us a like or a comment in the video section here, or on Twitter or Facebook. So please tell a friend.